All right, diving in today, and we're going to tackle something that, might seem kind of basic at first glance, measurement.
Right.
But as we dig into this, and we're using the Stanford Encyclopedia of Philosophy as our main source here, this is like the ultimate philosophical resource. You'll start to see that it's actually way more complicated than you might think.
Oh, absolutely.
Yeah.
If you're really trying to think hard about knowledge,
Yeah.
and hey, listener, that's you.
Yeah.
Measurement.
Yeah.
It's kind of like, it's crucial.
Yeah.
It's how we go from like vague ideas to real solid data. Right?
Yeah.
But philosophers, they've been poking at this for centuries, asking, like, what does it really mean to measure something? How do we breach that gap between the world as we experience it and the numbers we slap on it?
Totally. And especially for someone like you who's, clearly loves to geek out on understanding. The very act of quantifying the world, like how we take something that's qualitative, like a feeling, and turn it into something we can count, that's got to be fascinating.
Right.
So think of this deep dive as like a backstage pass to the whole philosophical brawl over measurement.
Yeah.
Without you having to go read like all those dense original texts yourself.
Right.
We'll do the heavy lifting. So our mission, if you choose to accept it, is to distill these big philosophical ideas about measurement. Like, what can we even measure in the first place?
Mm-hmm.
And what are the huge, like, head scratchers that philosophers have been wrestling with about this over time?
Yeah. And to really get this, I think it helps to start way back. Like, our sources take us all the way back to ancient Greece, Euclid.
Oh, yeah, Euclid.
Geometry, dude.
Okay, Euclid. So beyond all those triangles and parallel lines, he was messing around with measurement too.
He was, yeah.
Yeah.
So he had these like fundamental ideas about it.
Yeah.
He said that one magnitude measures another if the second one is like a whole multiple of the first one. So picture like, using a stick to measure a line, right? You're seeing how many times that stick length fits into the line.
Okay, yeah.
He also talked about things having a common measuring unit. And then there's this crazy idea of incommensurable magnitudes, which, whoa!
Incommensurable magnitudes. All right, break that down for me.
Yeah, so that was a big deal. It's like, the side of a square and the diagonal of that same square, they can't be expressed as a simple fraction of each other. That discovery was huge.
Yeah.
It showed that this simple idea, like, oh, one thing measures another, wasn't the whole story.
Right.
It forced them to realize that their math tools, they needed an upgrade to really grasp these magnitudes. It was a real shakeup in how they thought about geometry and numbers.
So basically, like, our tools weren't good enough to get at the truth of how these things relate to each other.
Yeah.
Okay, so from ancient Greece, let's jump ahead to Aristotle. He was all about bringing order to things.
Oh, yeah, Aristotle.
And his big thing was drawing this line between, like, quantities, which are things we can measure, like numbers, lines, time, places, and qualities, which are more like justice, health, how hot something is, that kind of stuff.
Yeah, and his view is pretty strict. Like, for quantities, he thought they could be equal. Like, one line could be the same length as another or longer, right? Unequal.
Yeah.
But you can't really have degrees of a quantity in the same way you have degrees of a quality. Like, you wouldn't say something is more 2 meters long than something else.
Yeah.
That doesn't make
Yeah,
sense.
you're either 2 meters long or you're not.
Exactly. But with qualities, they can definitely have degrees.
Sure.
You can be healthier or less healthy,
Right.
But they don't have that clear-cut equality or inequality like quantities.
Okay, so Aristotle's trying to put things in these neat boxes, quantities over here, qualities over there.
Right.
But our sources suggest that this didn't last forever. Like the medieval folks, they started poking holes in that.
Oh, yeah?
We got Duns Scotus and his addition theory. What was that about?
Well, he's suggesting that, like, when the intensity of a quality changes, it's like you're adding or taking away tiny bits of that quality. Imagine slowly turning up the volume on a speaker. You're adding little bits of sound intensity.
Yeah, I get that.
And then Nicole Resme comes along, and he's like, hold my beer. And he starts using these geometrical diagrams to actually represent visually how these qualities change over time, like velocity and how fast something is moving.
Okay.
This was huge because it hinted that you could think about some qualities mathematically, which was a big shift, and really laid the groundwork for all those quantitative laws in physics.
So Aristotle's neat little categories are starting to crumble.
They are, yeah.
All right, then we get to Leibniz.
Oh, Leibniz, yeah.
What was he on about?
So he had this idea called the principle of continuity, which basically says nature doesn't do sudden jumps, right? Everything's changing smoothly and gradually. And he thought this applied not just to things like physical dimensions, but to our experiences too. Like the difference between a whisper and a shout, it's not a sudden leap, it's a gradual increase in sound intensity.
Oh, okay.
And then Kant built on this with his distinction between extensive and intensive magnitudes. So extensive magnitudes, like how long your table is, you can understand the whole thing by adding up its parts. You can measure it bit by bit in space and time.
Right.
But intensive magnitudes, like the warmth of your coffee, you grasp that all at once.
Yeah.
You understand how intense it is by thinking about it getting weaker and weaker until it vanishes.
Okay. Yeah.
Like approximating its opposite.
So you're approaching zero.
Right, exactly.
Okay, so this distinction between extensive and intensive, it feels pretty clear cut, right?
It does, yeah.
But then we hit the 19th century and wow, science just explodes. All these discoveries,
It gets messy.
they really complicate things.
Yeah.
We have thermodynamics, heat and energy,
Right.
wave optics, which is all about light.
Uh-huh.
And these fields start showing that qualities like temperature and color are actually tied to these underlying things we can measure, like the average speed of molecules for temperature,
Right.
or the wavelength of light for color.
Exactly.
And all of a sudden, Aristotle's neat division starts to break down.
Yeah, like it turned out some qualities could be tied to measurable physical stuff.
Yeah, and it's not just in physics, right?
Sure.
This is happening all over. Like in early psychophysics, where they were trying to figure out how physical stuff like light and sound relate to our senses.
Right.
They started to suggest that even our subjective experiences, like how bright a light appears or how loud a sound is, could be broken down into these like tiny, just noticeable differences.
Yeah, like our sensations had a hidden quantifiable structure too.
Right. So all this new science, plus all the progress in formalizing mathematics, really pushed people like Maxwell, Helmholtz, Mach, Poincaré, Holder, all these big names, to dive deep into the mathematical foundations of measurement.
Yeah, they started asking these really basic questions like, how can we use numbers to actually represent the world in a way that makes sense, that's reliable?
Right.
And that's the groundwork for what we now call measurement theory.
Okay, so measurement theory. What's the big burning question at the heart of all this?
Well, it's like this. When we assign numbers to things, how can we be sure those relationships between the numbers actually tell us something real about the relationships between the things we're measuring?
Right.
Just because we can stick a number on it doesn't mean that number means anything useful about the real world.
Yeah, that makes total sense. Like, Celsius, we talked about that earlier.
Yeah.
The difference between 10 degrees and 20 degrees is the same as the difference between 30 degrees and 40 degrees.
Right.
But that doesn't mean 20 degrees is twice as hot as 10 degrees.
Exactly. So measurement theory is about figuring out, like, what are the assumptions baked in when we use math to describe the world? And then understanding, like, where does that approach break down? What are the limits?
Okay. And one of the key ideas here is that the parts of a mathematical structure that actually mean something in the real world are the parts that mirror, that reflect the real relationships between the things we're measuring.
Right. It's like if the idea of greater than in math consistently lines up with the idea of longer than in the real world, then that's a meaningful numerical relationship for length.
Got it.
And this mirroring, this mapping, that's what we call a measurement scale.
But measurement theory, it's not just one unified thing, right? There are different camps within it.
Oh, yeah, definitely. Like one major point of disagreement is, what are the actual things we're measuring?
Yeah, good point.
Are we talking about objects you can hold in your hand?
Yeah.
Or are we talking about, like, your subjective experience of that object?
Right.
Or maybe it's like abstract theoretical stuff. Or even like fundamental properties that exist, like out there in the universe on their own.
Right. So it's really getting at this question of what's real, what are the fundamental building blocks of the universe?
Exactly. And another big debate is about the kind of evidence you need to make these mappings between the world and numbers, which leads to some really cool questions like, can we actually measure happiness? Can we quantify that?
Okay, so our source mentions that early on there was some agreement that measurement was about assigning numbers to magnitudes, like Helmholtz, Russell, Campbell. They all seem to be on board with that basic idea.
Yeah, but then the big question becomes, like, which ways of assigning those numbers are actually valid?
Right.
What are the ground rules for that?
And how do we know if it's meaningful?
Right. So early theorists like Helmholtz, Holder, and Campbell, they thought the key was whether the math we do with the numbers actually reflects what we see happening in the real world with the things themselves.
Mm-hmm.
Okay, so like if you take two sticks and you physically put them end to end, that corresponds to adding their lengths together.
Exactly, yeah. So they came up with these sets of rules called axioms to describe the way these things work in the real world. And they use those axioms to prove that if a magnitude has certain properties, like you can order things, this one's bigger than that one, and there's this operation, like putting the sticks together, that acts like addition.
Yeah.
Then you can create a numerical representation where adding the numbers is like physically combining the things themselves.
Okay.
And Campbell called this fundamental measurement because you're not relying on measuring something else first.
Right.
So things like length, weight, volume, those were seen as fundamental magnitudes because you can kind of build them up from putting together equal units.
Okay, so fundamental magnitudes are the ones that you can kind of like directly measure by adding up units.
Right.
And then you've got derived measurement, where you're not directly adding up units, you're figuring out the value of something based on its relationship to those fundamental magnitudes.
Right, like measuring temperature by seeing how much mercury expands,
Yeah.
or finding density by dividing mass by volume.
Right, okay.
And it's interesting that this fundamental versus derived distinction, it's not quite the same as the extensive versus intensive thing we talked about with Kant.
Right.
It really depends on how you're measuring the operations, not just what the quantity is.
Okay, so it's about the method.
Exactly, yeah. And you could even imagine a derived magnitude becoming fundamental if we figure out a new way to measure it directly using that adding units method.
Okay,
So it's not set in stone.
interesting. Our source mentions that later on, folks like Ellis and Keiberg kind of revised this whole fundamental versus derived thing. So it sounds like that first categorization, it wasn't the final word.
No, not at all.
Hmm.
And then comes S.S. Stevens, who gave us this super influential way of classifying measurement scales. Nominal, ordinal, interval, and ratio.
Okay, I've heard of those.
Yeah.
But remind me what they are again.
All right, so nominal scales are just for putting things into categories. No order or anything, like labeling different types of trees.
Okay, yeah.
Ordinal scales, now you have order, like ranking students from top to bottom.
Yeah.
But the difference between rank 1 and 2 might not be the same as between rank 2 and 3.
Right, like the top student might have aced everything, but the next few are all really close together.
Exactly. Then you've got interval scales, where the intervals are equal, like Celsius or Fahrenheit.
Yeah.
The difference between 10 and 20 degrees represents the same change as between 20 and 30.
Okay.
But 0 on those scales is arbitrary. It doesn't mean nothing.
Yeah.
So you can't really say 20 degrees Celsius is twice as hot as 10 degrees
Yeah.
in a fundamental sense.
Got it.
And finally, ratio scales, like Kelvin for temperature or length, they have a true 0 point.
Right.
So now you can make those ratio statements. 2 meters is twice as long as 1 meter.
Makes sense.
And Stevens later added absolute scales for things like counting, where there's like a natural unit. And you can't really change the scale without messing up the whole meaning.
Okay, so this whole classification of scales, it wasn't just for organizing our measurements, right? It also told us what math we could do with those numbers.
Oh, totally. Stevens argued that the type of scale limits what transformations you can do to the numbers without losing information. Like you can add a constant to an interval scale, but you can't multiply it by a constant.
Right.
This classification was huge. Everybody used it. But naturally, it caused some arguments, too.
Of course.
Like, can we even call nominal and ordinal scales measurement?
Right, because they don't have all that math power that interval and ratio scales have.
Exactly. So it really forced people to think, okay, what's the bare minimum to even call something measurement?
Yeah, what are the essential ingredients?
Right. And this whole debate ties into a really old question. Can we measure sensations?
Ooh, like how loud something sounds or how bright a light is.
Yeah, and that was a huge point of contention for a long time.
Okay, so where did that debate start?
Well, we got to go back to Gustav Fechner. He was one of the pioneers of psychophysics.
Okay.
And he tried to quantify sensations based on these just noticeable differences in stimuli.
Right.
He assumed that each of those differences was like a step up in the intensity of the sensation.
Okay.
And this led to Fechner's law, which said there's this logarithmic relationship between how intense a stimulus is and how intense the sensation feels. So it suggested that maybe our subjective experiences could be mapped onto numbers.
Okay.
But Campbell wasn't buying it. He said, nope, fundamental measurement needs this thing called empirical concatenation. You got to be able to physically combine things in a way that's like addition. And you can't really do that with sensations.
Right. You can't take two sensations of loudness and stick them together.
Exactly. He also thought the psychophysical laws, like Fechner's law, weren't strong enough to build derived measurement on. He said just having sensations in order isn't enough to justify giving them numbers with all those fancy math properties.
Right.
And then Stevens comes along, and he's got this, more flexible view. He's like, measurement, that's just assigning numbers according to rules. As long as it's consistent and not random, we're good.
Okay.
He emphasized these matching operations, like connecting a temperature to the height of mercury in a thermometer, or having people compare sensations and assign numbers based on that comparison.
Okay.
And he totally rejected the idea that numerical scales had to perfectly reflect some pre-existing structure in the world. For him, scales were just tools. We choose the best tool for the job based on how well they help us understand the data.
So Stevens was more about practicality, not so worried about whether the numbers perfectly reflected some underlying reality?
Yeah, exactly. And this sets the stage for the representational theory of measurement, or RTM.
RTM. Okay. So that's the attempt to bring all these different ideas about measurement together.
It is, yeah. And the work of Patrick Sapis was huge in developing this. RTM says that measurement is basically about building these mappings, specifically homomorphisms.
Homomorphisms.
Yeah, it's a fancy word, but basically it's a mapping that preserves the relationships between things.
Okay.
So you have these empirical relational structures, which are the things we're measuring and how they relate to each other in the real world.
Right.
And then you map those onto numerical relational structures, which are sets of numbers and their mathematical relationships. And the measurement scale is that mapping.
So it's showing how the relationships we see in the world can be represented by mathematical relationships between numbers.
Exactly. And RTM really fleshed out the assumptions behind the different types of scales that Stevens came up with. It showed how the empirical properties of the thing you're measuring determine what kind of scale you can use. And on measuring subjective experiences, RTM took a middle ground. It agreed with Campbell that we need solid evidence and clear rules for assigning numbers.
Right.
But it didn't necessarily need that physical combining thing for fundamental measurement.
Okay, so that's where this additive conjoint measurement comes in, Luce and Tukey.
Yeah, exactly. They showed you can have fundamental measurement even if you can't physically combine the things you're measuring. Like, imagine how the temperature and pressure of a gas both affect its volume.
Okay.
By looking at how those two things together influence the volume, you can create scales for temperature and pressure, even if you can't directly add them together physically. And this idea can be expanded to more than two attributes, which meant that a lot of psychological stuff, which you can't really physically combine, could potentially be measured fundamentally.
Interesting. So RTM kind of expanded what we thought of as fundamental measurement.
Yeah, it did.
Okay, we've been talking about the math side of measurement, but what about the words themselves? Like, what do we even mean when we say length?
Right. That's where operationalism and conventionalism come in.
Okay, so remind me, what's the difference between those two?
So if you're a realist about a term like length, you think it points to something real in the world, whether we measure it or not.
Okay.
But operationalists and conventionalists say, hold on, how we actually use those words, like how we decide what counts as length in a specific situation, that depends on the choices we make, especially how we choose to measure it.
Okay.
So operationalism, in its purest form, says the meaning of a concept like length is totally determined by the way we measure it.
Okay.
Like Percy Bridgman was a big fan of this idea. He even went so far as to say that if we measure length two different ways, we're actually talking about two different things, like length as measured by a ruler versus length as measured by radar.
Wow, that's pretty extreme.
It is, yeah. But he did say that if different ways of measuring always gave the same result, then fine, we can call them both the same thing for convenience. Operationalism was really influential in psychology because behaviorists, like B.F. Skinner, saw it as a way to make mental concepts, which are tricky, more concrete, tie them to observable actions. And S.S. Stevens was also into operationalism, wanting to make sure psychological concepts were empirically grounded.
Yeah.
But even Stevens probably wasn't a hardcore anti-realist. He was probably more focused on the methodology.
Right, so it's about having a clear, repeatable way to get at these concepts.
Exactly. But operationalism got hit with some pretty big criticisms.
Like what?
Well, one problem is that it automatically makes any well-defined measurement a reliable way to figure out the property,
Okay.
which isn't always true. And then there's the problem of defining abstract theoretical concepts operationally. Like, how do you come up with a set of operations to define fragility?
Right.
So Carl Hempel, he really pointed out the issues with trying to do that for all these complex concepts.
Okay.
And because of these problems, strict operationalism isn't really popular anymore. And then you've got conventionalism, which says, okay, there are definitely human choices involved in how we use these terms, but it's not just about the operations.
Right, so it's a more nuanced view.
Yeah, like Ernst Mach, he pointed out that choosing mercury for thermometers, that was a convention, a human choice.
Okay.
And that choice affects how we define equal intervals of temperature.
Right.
And Henri Poincaré, he argued that even our basic ideas about time and space, like that they're uniform, involve conventions.
Mm-hmm.
It's based on our preference for simplicity and the convenience of Euclidean geometry. And then the logical positivists, they took this even further with these coordinative definitions or correspondence rules.
Right.
They saw these as like pre-agreed upon links between our theoretical terms and the stuff we can observe, bridging the gap between abstract theories and real-world experience.
Okay.
Rudolf Carnap and Hans Reichenbach were big names here.
Yeah.
Reichenbach had this famous example of this statement, a measuring rod stays the same length when you move it. He said it's impossible to verify that completely, but we accept it as a rule, as part of how we define equal length in different places. And these rules are seen as additions to our definitions, not replacements.
So it's moving away from the strict idea that the operation defines the concept and towards a view where our choices about how we measure things play a role in how we understand those concepts.
Right. And this sets the stage for realism in measurement, which offers a different way of thinking about it altogether.
Okay, so what does it mean to be a realist about measurement?
Basically, it's the view that measurement is about trying to figure out some objective property or relationship that's out there in the world. Now, objective doesn't necessarily rule out things like mental states.
Okay.
A realist could believe in the objective reality of, say, how intense your pain is.
Right.
But it means those things exist independently of us, our beliefs, our conventions, our methods of measuring. And the key here is estimation.
Okay.
Like we're acknowledging that measurements are usually approximations, not perfect reflections of the truth.
Right.
And realists are mostly interested in learning about those underlying properties and relationships, not just assigning numbers to things.
So if I'm a realist, I'd say the length of this microphone cord exists regardless of whether I measure it.
Exactly. And most realists also believe in property realism, meaning those measurable properties are real things, and they have a structure that explains why our measurements work so well. Like the fact that we can put objects in order by length and that combining lengths works like adding numbers, that suggests length is a real property that acts like positive real numbers.
Okay, that makes sense. Our source mentions a more specific kind of realism for Mitchell. He says numbers themselves are just ratios between quantities that exist in space and time, and that measurement is all about figuring out those ratios.
Yeah, that's a particular flavor of realism.
Okay.
And generally, realists contrast their view with the strong operationalist and conventionalist views. They say if quantities didn't have real values, independent of how we measure them, then ideas like measurement accuracy and error would make sense. Why would we even try to make our measurements more precise if there wasn't some truth we were trying to get closer to?
Yeah, it'd be pointless.
Right. And realism also explains why different methods often converge on similar results. It's because they're all trying to get at the same underlying reality. Plus, the fact that our theories guide how we design and interpret our instruments suggests that these quantities have a kind of priority. They're out there, waiting to be discovered.
Okay, so realists also have their own take on the math theories of measurement.
Yeah, they accept the axioms and stuff, but they interpret them differently. They see them as referring to universal properties, not just the specific objects we're measuring.
Okay, so instead of talking about the length of this specific microphone cord, they're talking about the property of length itself.
Exactly. And people like John Mundy and Howard Sawyer have reinterpreted the axioms of measurement theory in this way.
Okay.
They argue this makes it more powerful, more general.
And it turns measurement theory into a scientific theory itself, right?
Yeah, it's making claims about the structure of the world. And then there's Stephen Wolf, who uses the representational theory of measurement to propose a kind of structuralist realism.
Okay.
In this view, quantities are like relational structures with certain mathematical properties.
Okay.
But they don't have to be tied to numbers in a fundamental way.
Interesting. Okay, so we've looked at the metaphysical side with realism, but there's also the information perspective. That brings us to information theoretic accounts.
Yeah, so these accounts see measurement as kind of like communication.
Okay.
The measuring instrument is like an information machine.
Okay.
It takes the state of the object as input, encodes it into a signal, transmits that signal, and then decodes it to give you the reading.
Okay, so like sending a message.
Exactly. And just like with communication, how accurate the measurement is depends on the quality of the instrument and how much noise there is.
Right.
And we can use ideas from information theory to think about this, like how much information does a measurement give us?
Right.
Well, it's about how much it reduces our uncertainty about the object's state.
Okay.
Some philosophers, like Finkelstein and Maury, have suggested we could even combine information theory and measurement theory.
How would that work?
So information theory would handle the syntax of measurement, like how we manipulate symbols, and measurement theory would handle the semantics, like what those symbols actually mean.
Okay.
But Maury also pointed out a difference between measurement and communication. In communication, the sender knows the message perfectly before sending it. But in measurement, we never know the object's state perfectly beforehand.
Right, that's a key difference. And it's interesting that these information theoretic ideas about measurement came from metrologists, the people who deal with the practical side of measurement.
Yeah, it makes sense. They're the ones worried about how reliable and accurate our instruments are.
Makes sense.
And Bos van Frassen, he has this newer information-focused view.
Okay, what's his take?
He says measurement happens on two levels. First, there's the physical interaction between the instrument and the object, which gives us a reading.
Right.
Then there's the abstract level, where our scientific theories represent all the possible states of the object.
Okay.
So Van Frassen says measurement basically pinpoints the object within that space of possibilities, which reduces our uncertainty and gives us information.
Okay, so it's narrowing down the possibilities.
Exactly. And his view is different from the earlier ones because he directly includes the role of our theories, and he doesn't rely on that Shannon-Weaver model of information transfer.
Okay.
It's more nuanced.
Okay, so now we're getting into some of the more modern thinking about measurement with model-based accounts.
Yeah.
These seem to really focus on how important our theories and statistical models are for understanding measurement.
Right. This view has become really popular in the last couple of decades. It says measurement happens on two levels.
Okay.
First, there's the physical stuff, the interaction between the object, the instrument, and the environment. Then there's the abstract level, where we build models to represent that whole process, often making simplifying assumptions.
Okay.
And the goal is to assign values to the parameters in the model that correspond to the things we're trying to measure.
Okay.
It's about creating a coherent picture.
And this approach came from looking at how scientists actually measure things in the real world,
Right.
especially in metrology.
Yeah, that's right. Philosophers started paying attention to what metrologists were doing, how they dealt with calibration, standards, and uncertainty.
Because those are all crucial parts of measurement that the older theories didn't really address.
Exactly. Like, RTM was mostly focused on the math of scales, but model-based accounts say that building scales is just one part of the process.
Right.
There's so much more going on.
So in this view, a measurement isn't just what you read off the instrument.
No, not at all.
It's about building a model that includes everything involved. The object, the instrument, the environment, and any other interaction. And the model has parameters, and the things we're trying to measure, those are represented as specific parameters within the model.
Right. Host speaker.